Hello and welcome to all students. Students, we are in the topic of structure of atom, and in this our topic, in our last lecture, we have seen the shapes of different orbitals. In it, we have seen the 1s and 2s orbitals, its corresponding shape, as well as we have also seen the shapes of 2p orbitals. Students, in this point, we have also covered the shapes of d orbitals. Now, if we look at the shapes of 1s and 2s orbitals are in spherical shape, while the shapes of p orbitals for 2p orbitals are having three different types: 2px, 2py, and 2pz. Now, students, if you look at its corresponding shape, it will appear as a dumbbell shape, and if you look at the d orbitals, they get divided into five different types: dxy, dxz, dyz, and dz x square minus y square and dz square, and their corresponding shapes also shown in this diagram. Now students, along with this, some problems are also asked in your exam, like this: if an atom has a 2 electrons in its corresponding 4s orbital, then what we have to write is nothing but the values of the 4 quantum numbers for each of them. So this is the solution for it. Suppose for 4s orbitals, 4 stands for the principal quantum number n, and s stands for the subshell having the value of azimuthal quantum number L is equal to 0. In the s subshell there is only one orbital and has the magnetic quantum number ml is equal to 0. Now students, the 2 electrons in this orbital have opposite spins, thus the 4 quantum numbers of 2 electrons in 4s orbital are like this. For the identity of electron first, n is equal to 4, L is equal to 0, ml, that is magnetic quantum number, is 0, and it has the spin quantum number, that is value plus 1/2, and another electron in the same subshell with opposite spin, therefore its value we will get is minus 1/2. So this is all about that we have seen for electrons. If the 3 quantum numbers of any electron, the identity of any electron is same, then the 4th quantum number will be different. So this is the case for a problem when such questions may be asked in your exam. Now students, we will now going to look at the different principles for the filling up of electrons. In our last lecture we have also seen the energies of orbitals and above principle and its corresponding diagram. Student, this is the energy sequence. First we should fill the electron in the lowest energy level, that is 1s. Then we are going to fill the electrons in the next corresponding subshell, that is 2s. Then after filling it, we should go for the higher energy, that is 2p, 3s, 3p, 4s, like this. The energy sequence is shown in your textbook with the diagram as well as the sequence. Now students, dependence of orbital energy on n plus L value. If you look at this table 4.9, you will notice here the orbital energy is going on increasing from 1s to 4p, and the corresponding principal quantum number values, azimuthal quantum number values, we have taken here for understanding. Suppose if the orbital is 1s, for it corresponding the principal value will be n is equal to 1 and corresponding azimuthal quantum number will be 0. So if we apply this rule, n plus L, we will get its corresponding value will be 1, means This is nothing but the dependence of orbital energy. For if you look at 3D, principal quantum number will be n is equal to 3. Its corresponding azimuthal quantum number, that is n minus 1, that is L is equal to n minus 1, means L is equal to 2. So you will get its corresponding value 5, means it has the capacity of 10 electrons. So 5 degenerate orbitals are present in its corresponding orbital. Now students, if we look at the increasing order of energy of orbitals, as if we seen in the previous section, the increasing order of energies of orbital is decided by the n plus L value. Therefore n plus L value, which is very important, as we have seen in our previous table, electrons in the ground state atom are filled in the orbitals in an increasing order of energy, shows a useful method to remember this increasing order of orbital energy. Now students, according to the Pauli exclusion principle, the capacity of an orbital to accommodate electrons is decided by Pauli exclusion principle. What this principle states us: no two electrons in an atom can have the same set of 4 quantum numbers. What does it means? We have seen with the help of problem now only. Another way to state this Pauli exclusion principle is only two electrons can occupy the same orbital and they must have opposite spins. So this is the another way to express this principle. And students, with the help of one of the problem from this previous point, we have seen in the problem. If you look at this table, for electron 1 and 2, you will notice here 3 values are same, but the 4th value will be different. Now students, we are going to look at the example for this Pauli's exclusion principle. Here only they are mentioned in your textbook. Look at this. This principle can be illustrated with the helium atom, which is having atomic number 2. Its electronic configuration is 1s2. Look at this table 4.10 students. You will understand what this principle can states us. If we look at the electrons which are present in the helium, and these electrons has the identity. If you look at the set of 4 quantum numbers, that is first principal quantum number, azimuthal quantum number, magnetic quantum number and spin quantum number, their corresponding values we have taken in this table for first electron and second electron. You will notice here the n value will be 1 for first and second electron, L values will be same 0 0, and magnetic quantum number also will be 0 0. But if you look at the identity of the spin for this for the electrons which are present in the helium, the spin quantum number will be different for both the electrons. For first electron it will be plus 1/2, and for another electron it will be minus 1/2. Now students, this implies that two electrons in the same atom have always different set of quantum numbers. That means the set of NLMS is the same and the MS is different, means spin quantum number will be different. Now student, if you look at the next principle for the filling of electrons, which is nothing but the Hunds rule of maximum multiplicity. Now student, this is also very important for the filling up of electrons in the corresponding orbitals. So what does it explains? Hunds maximum multiplicity rule, we can say in another way: pairing of electrons in the orbitals belonging to the same subshell does not occur unless each orbital belonging to that subshell has got one electron each. Now students, we will understand this rule by considering one of the example. Now students, look at this one of the example for filling up of p subshell. Now students, p subshell has 3 degenerate orbitals, means we have already seen in the shape of p orbital 2px, 2py and 2pz. Here pairing of electrons starts when the fourth electron enters the p subshell. The electronic configuration of 4 electrons occupying p orbital, then it will be like this. Now students, look at this square. In this square you will notice that the electrons which are filled in the p subshell are in number 4. First 3 electrons are filled up with the vertical, or we can say in upward direction, but the fourth electron which is entered in this subshell is filled in the downward direction. And the next part which is shown in your textbook, if the 4 electrons are present, then we cannot fill like this. This is the wrong method, and the previous one which is shown here, the pairing should be like this. Means what does this Hunds rule explains us? First fill the electrons singly, then go for the pairing. Half filled and fully filled set of degenerate orbitals has extra stability. So this is the principle or the rule for the filling up of electrons. Now students, if you look at the electronic configuration of atoms and its corresponding representations, we can take it with the different examples. Now students, if you look at the representation of electronic configuration for hydrogen atom, its symbol we can represent like this, H1 at the base. What it indicates? It indicates the atomic number, and the orbital notation will be like this, 1s1, and the orbital diagram for its corresponding representation will be like this. That is, in a single square we have to show the one electron with the upward direction, and in helium the capacity of 1s orbital, if it is as it is 1 electron which is present in the upward direction and another electron which is in the downward direction. So this is the capacity of 1s orbital, that is carrying 2 electrons. Suppose if we take the example of lithium, here 1s2 2s1 means 1s orbital is completely filled, and the next electron which is goes into the next orbital, suborbital, that is what we can say, after filling electron in the 1s, electron will enters into the now higher energy level, that is 2s. Therefore we have shown it with upward direction, that is single electron. So this is the representation of filling up of electrons in the corresponding subshells. Now likewise, if we take an example of any element, then we have to fill in this proper order. Now students, some of the elements in the periodic table are present which shows the anomalous behavior. Out of them, copper and chromium, these are the elements which shows the anomalous behavior, means its expected electronic configuration and that of the electronic configuration which is now we are going to write will be different. So these are the 2 points which explains us. Atomic number of chromium is 24. Expected electronic configuration is like this: 1s2 2s2 2p6, 3s2 3p6, 4s2 3d4. But here 3d is not half filled, hence to acquire the higher stability, electron now will enters from 4s into the 3d, because half filled orbital is more stable and completely filled orbital will be more stable. Therefore, due to both the reasons, the chromium and the copper will shows the different electronic configuration than that of the expected one. Now students, if you look at the next point of this chapter is nothing but to write the electronic configuration of the first 30 elements, and students, in your textbook they have provided it with, but Along with that, you have to practice it by taking the elements by taking the elements different than that of these 30 elements. Means after 30 you can also find many elements, and for that you have to write the electronic configuration. And to write this electronic configuration, you should use all the principles which is provided in this chapter, as well as you have to take the help of Bohr principle to fill the electrons with the increasing order of their corresponding energy levels. So this is all about in our today's lecture, and thank you very much.